this video, we're going to review a couple of topics associated with functions that you're going to need for calculus. So specifically, we're going to look at something called the difference quotient, and then we're also going to talk about function composition and then function decomposition. So let's start with the difference quotient. First off, what is the difference quotient? It is an expression that's defined for functions that's specifically related to a concept in calculus called the derivative. So you'll talk more about what the derivative is when you get to calculus. We're going to start with one component of it called the difference quotient. So given a function f of x, the difference quotient for x is defined as the following expression. It's the expression f of x plus h minus f of x all over h. This is the expression that we call the difference quotient. So as you first look at it, it probably looks pretty arbitrary, but it actually has a context, it actually has a very specific meaning. So logically speaking, this expression is equivalent to the formula for the slope of a secant line that's drawn passing through the graph of f of x. So let's look at an illustration of what this would look like. So suppose this is the graph of our function f of x. So specifically, the curve represents f of x. Okay. This particular line that's drawn through that curve is what we call a secant line. So a tangent line will intersect the graph at one point. A secant line will intersect the graph at more than one point. So notice this line intersects this function's graph at these 2 points. So what we now want to write is an expression for the slope of this secant line based on the fact that this line is passing through the function f of x. So how we write this expression is going to depend on how we label the coordinates of these 2 points on this line and on this function. So one way we could label these points is using x1, x2 using subscript notation. So using that notation, we could call this particular x value x1, and we could call this value x2. Now we could also call this y1 and y2, but because these two ordered pairs represent points on the curve f of x, we can also label them using function notation. So if this is x1, then the associated output we could also call f of x1. And then if this is x2, the associated output could also be called f of x2. So rather than calling them y1 and y2, we can call them f of x1 and f of x2. So if we use this particular notation, that means that the slope of this line, change in y over change in x, would be f of x2 minus f of x1 divided by x2 minus x1. This would be the formula for slope using this particular notation for our ordered pairs. Okay. I want to look at another way that we could label these coordinates, and this is going to lead us to the definition for the difference quotient. So rather than calling this particular x value x1 and this value x2, I'm going to take this particular one, and rather than calling it x1, I'm just going to call it x instead. So this will be a different notation for this particular x value. Well, this particular x value in terms of x could also be labeled as x plus h. In other words, if we start at x and add some distance that we can call h, let's see, you probably can't see that. Let me move that up. There we go. We add this distance that we call h, then this would take us to a new x value that we can call x plus h. So it's just this x value plus some additional distance that we're calling h. Well, if we change the labels for our x values, then we'll see corresponding changes for our y values. So rather than calling this f of x1, since we're now calling our input just x, we can call this location f of x. And then rather than calling this y value f of x2, because it's now associated with the x value that we're calling x plus h, we could call this f of x plus h. So then the question is, how would this change our expression for slope if we use all of this new notation? Well, slope is still defined in the same way, but now we're using different notations for our x and y values. So in place of f of x2, we would call this f of x plus h. And then in place of f of x1, we'll now call this just f of x. So f of x plus h minus f of x. And then change in x, well, this is now our x2, this is our x1, so our denominator would become x plus h minus x. We can clean up this denominator. There's nothing we can specifically do in the numerator. These are not like terms, they don't combine. But notice in the denominator, we have this common term of x. So positive x, negative x combine, leaving us with h. So the simplified version of this slope expression would be f of x plus h minus f of x, all divided by h. And this particular expression, this is what we call the difference quotient. So ultimately, the difference quotient is just a way of writing the slope of a line, specifically a line that's drawn passing through a function's graph. So if we were to take this one step further and shrink the distance between x plus h and x, in other words, imagine sliding this point along the curve and then drawing the resulting secant line. If we were to take h and shrink it down, bring x plus h closer and closer and closer to this value x, that's going to be the fundamental concept behind what we call the derivative. So more about that once you get to calculus. What we're going to focus on now is just the difference quotient. How do we find the actual difference quotient for a function, and then how do we simplify that expression? Okay. So simplification, depending on the type of function we have, can be relatively complicated. But if we keep a couple goals in mind, it will make the simplification a little bit easier. So among other things, by the end of the simplification of our difference quotient, we should typically be able to eliminate the h in the denominator of the expression. So as we simplify the numerator, a bunch of terms will typically be canceled out because we have like terms that are equal and opposite. And then what we'll be left with will be something that can eliminate the h in the denominator, something that will allow us to divide that out. So by the time we have a full simplification, in most cases, this h should be eliminated. That's typically an indication that we've simplified the difference quotient correctly and that we've gotten down to the full simplification. So let's look at a couple examples. So here's our first function, f of x. Our directions are first to find f of x plus h, in other words, our first term in our difference quotient. And then based on that, we want to build it to get the difference quotient for the actual function. And then most important part, we want to take that expression and we want to simplify it fully. So let's start with a linear function, something really basic. So f of x is 3x minus 5 in this case. So if we want to evaluate f of x plus h, this is just saying take the rule for f and then substitute in the specific input of x plus h in place of our generic input x. So this would be 3 times x plus h minus 5. Now we need to simplify that down. So distribute your 3. So we have 3x plus 3h minus 5. And none of these are like terms, so that would be the full simplification for this particular expression. Okay, now we want to take our expression for f of x plus h, and we want to put that into our expression for the difference quotient and find the full expression for the difference quotient based on this function f of x. So f of x plus h, we can substitute in this expression. Now as we substitute, make sure you put parentheses around everything that you're substituting into your expression. So as we plug in f of x plus h, we're going to put parentheses around it. Then we're subtracting just f of x, no changes made. So we're adding in, subbing in 3x minus 5 in place of our f of x. And again, we want to put parentheses around it. In this case, these parentheses are going to be important because they're going to help us take care of these two signs correctly. And then we are dividing all of that by h. Now what we want to focus on now is simplifying the numerator. You will find 99% of the time this particular expression over here, f of x, can be canceled if we combine like terms with the terms we got from f of x plus h. So you're looking to combine all of your like terms in your numerator, and that's going to put you in a good position to reach that ultimate goal of eliminating the h in the denominator. So we have a 3x here minus a 3x, so those are like terms. They're also equal and opposite, so they reduce to 0. We also have a negative 5 minus another negative 5, in other words, plus 5. That's why those parentheses are important. That turns that subtraction into an addition. Also, like terms, also equal and opposite, so they're eliminated. So notice everything in parentheses over here went away by combining all of our like terms. So the only thing we're left with in our numerator is going to be that 3h. So our numerator reduces to 3h, and then we still have that h in the denominator. Now this puts us in a good position because notice we now have a common factor of h, so we can divide out that common factor, which leaves us with 3. So based on the function f of x, if we evaluate the difference quotient expression, it evaluates and simplifies to a 3. Okay, now let's look at a couple more examples. Let's look at a couple slightly more complicated functions. So let's look at a quadratic function. Take our linear function, take it up one step. So our next function is defined as negative 2x squared plus 4x. So same directions, let's start with just f of x plus h. Simplify that first term in the difference quotient. So I'm going to take my rule for f. Each place I have an x, a generic input, I'm going to sub in this specific input, x plus h. So that's going to be negative 2 times the quantity x plus h squared plus 4 times the quantity x plus h. Okay, now we need to follow order of operations to simplify all of this down. So first thing we need to do is to apply our exponent. Be very careful here. It's so tempting to distribute that negative 2, but remember that's multiplication, and multiplication comes after the exponent when we talk about order of operations. So we need to apply that exponent before we distribute the negative 2. Now the 4 over here we can go ahead and distribute. So you can do a couple steps in one, or you can do each operation one at a time. So as we square this particular factor, keep in mind that's not x squared and then h squared. We have to FOIL this out. So if you need, take a moment, pause the video, make sure you can FOIL it out. This should be what you get. That should be the expression you get when you apply your exponent. Okay, and then we're distributing our 4, so plus 4x plus 4h. And then finally we need to distribute that negative 2. So we have negative 2x squared. Be careful, you have a 2 here, so negative 2 times 2 is going to be negative 4. So negative 4xh minus 2h squared, and then plus 4x plus 4h. Now again, we do not have any like terms, so we have 2 quadratic terms in x and h, 2 linear terms, x and h, and then 1 term that has both. So none of these 5 terms is a like term. We can leave this expression as is. Now we want to take this and we want to substitute it into our expression for our difference quotient. So that's going to replace our f of x plus h. Again, put parentheses around it when you substitute. So negative 2x squared minus 4xh minus 2h squared plus 4x plus 4h, okay, minus f of x as is, so minus, in parentheses, negative 2x squared plus 4x. And then all of that, don't forget this part, all of that is divided by h. Now, just as before, we want to focus on the numerator to start with. So we're looking for any like terms that can be combined. And as with the previous example, we're going to find that these 2 terms over here are actually eliminated. There's a like term that reduces them to 0. So we have negative 2x squared minus negative 2x squared, in other words, plus 2x squared, so equal and opposite. And then we also have a positive 4x minus positive 4x, so those 2 terms reduce as well. Notice nothing else combines, and we already determined that up there. So what are we left with in our numerator? We have negative 4xh minus 2h squared plus 4h. And then don't forget your h in the denominator. Okay, now what I want you to notice is each term in the numerator has an h in common. We also have a factor of 2 in common, but keep the goal in mind. The goal was to be able to simplify in such a way that we can eliminate the h in the denominator. Well, if we can take that common factor of h and factor it out of each of those terms in the numerator, then we should be able to reduce that h in the denominator. So factor out that common h. That's going to leave us with negative 4x from the first term. We have two h's here, so one left, so negative 2h, and then positive 4. And again, all of that is divided by h. So now that common factor divides out, reduces, and we're left with that remaining factor in our numerator. So our difference quotient simplifies to negative 4x minus 2h plus 4, and we can leave it like that. Okay, let's look at one more, kind of a special case. So in this case, we want to find the difference quotient's value for a rational function. Simplification of the difference quotient is going to be a little bit different here. We're going to need a little bit different algebra in order to simplify that numerator for the difference quotient. So let's start with f of x plus h. So I'm going to sub that in place of x. So x, we're subbing in x plus h, and then we also have a 1. Now notice in this case, having the parentheses versus not having them doesn't change the expression for the denominator. So we can actually just drop those off and we'll still have the same expression. Nothing combines in our denominator. We can't reduce anything from the numerator and denominator. So that's the fully simplified f of x plus h. Now we need to take that and sub that into our difference quotient. Now here we don't really need parentheses in the same way as we did before, because rational expressions automatically represent their own grouping. So anything that comes from our first term versus our second is automatically grouped just based on the fact that it's within a rational expression. Now from that we're subtracting f of x, so 1 over x plus 1, and then do not forget your denominator of h. So notice now we have fractions inside of fractions, so this is going to take a little bit more to simplify. Focus on the same things though. So first thing we want to do is simplify our numerator. We need to combine these two rational expressions. Now they don't have the same denominator, so as of right now they cannot be subtracted. We need to get a common denominator. Now these two factors are different. They have nothing in common. We can't say that the x plus 1 is something they have in common because we're treating the entire expression as one factor. So because these two factors are different, both are going to have to be present in our common denominator. So this particular expression is going to need the x plus 1, and this expression is going to need the x plus h plus 1. So you can think of it kind of like a cross multiplication in order to get the correct numerator for each of these. And then once we have that common denominator, we can combine our two expressions together. So the first numerator is going to be x plus 1, since that's going to be the factor we need for this particular expression. And then the second numerator is going to be x plus h plus 1, since that's the part that we need for that particular numerator. So combined together over our common denominator. Okay, and then all of that is divided by h. If getting the common denominator and combining the numerators together in one step was a little bit much for you, that's okay. Take a step back, pause the video, get the common denominator first. So this new numerator will be x plus 1, this new numerator will be x plus h plus 1, and then maybe combine them in a second step if you need to do that. Okay, we're going to leave this denominator in its factored form, the denominator inside the numerator, leave it in its factored form. but we do want to simplify anything we can in the numerator's numerator, if you want to think of it that way. So notice this x, so we have x minus x, again those are going to reduce, and then plus 1 minus plus 1, also going to reduce. So what are we left with? Well, we're left with our h, but watch your signs, be careful. Notice there's a subtraction here that will distribute to that h. So we have to include that as we simplify. So our new numerator here is going to be negative h, and then again leave that denominator in its factored form. X plus h plus 1, x plus 1. Now I'm going to combine a couple steps here. So that's the fully simplified expression in the numerator. Notice we're dividing by h. So ultimately it's fractional division. It's one fraction divided by something. Well, in order to execute the procedure for fractional division, we convert to multiplication. So we leave the numerator alone, change from division to multiplication, and then we're multiplying by the reciprocal of the denominator. So in this case, rather than dividing by h, we can think of this as multiplication by 1 over h. Now how does this benefit us? Again, the goal is to be able to cancel that particular h, to reduce it. So now we have this common factor that reduces diagonally. And again, trace that h. Here's the h, here's the h, and then when we convert it to multiplication, that's that particular h. It now reduces because we have that negative h in the numerator. So in the numerator, be careful, we're not left with 0. This now becomes negative 1, and this is a positive 1. So our final numerator is going to be a negative 1. And then our denominator is going to be x plus h plus 1 times x plus 1. And again, we're going to leave that in its factored form. Once you actually get to calculus, you're going to take each of these simplifications a step further, and leaving it in the factored form is going to be beneficial for the next steps you'll take. So that gives us a little bit of a taste of what the difference quotient simplification can look like. The more complicated the function is, it's typically a little bit more difficult to simplify the difference quotient. But the goal is ultimately the same. We want to simplify the numerator of the expression, and we want to be able to reduce something with the h in the denominator. So that's going to be our final difference quotient. Okay, let's switch gears, and let's talk a little bit about function composition and then function decomposition. So what is function composition? Function composition is using a function as the input for another function. So rather than plugging in a variable, plugging in a constant, we're actually plugging in one function into another. So the notation for function composition is this small open circle, looks kind of like a degree symbol. So we could read this as f of g, or f composed with g. What this ultimately means is that we're taking g of x as a function and we're making it the input for the function f. So another way to write this expression that really explains what's happening is like this. We're taking the function g of x, we're treating this as the inner function for our composition, and that is now the input for the function f. Now keep in mind, function composition is not commutative. If we change the order of the composition, these two functions switch, and in general we don't end up with the same expression. So we do have to adhere strictly to the ordering indicated by our composition. Now once we compose these two functions together and simplify the result, what we ultimately get is a new function, a new standalone function. Anytime we talk about a function, it's important to think about domain and range. Domain is the set of all inputs for which the function is defined, and the range is going to be the set of all outputs that we can get from those particular inputs. So if we compose our two functions together, resulting in a new function, that new function also has its own domain. But how we determine that domain is going to be a little bit more involved than how it is just looking at a function by itself. So the domain of a function composition takes into account two things. Number one, it takes into account restrictions for the inner function. In this case, we're thinking of that as the function g of x. And it also takes into account restrictions for the final function, what we get once we fully simplify everything down. So this term restrictions, what are we thinking about when we think of restrictions? Well, in most cases, for most functions, we can use any input we want. We can plug in any x value we want, and it's defined, we can find an output. There are a couple different situations where we attempt to plug in an input and we run into some issues. So one of them is if our function has a denominator. We have to make sure we're not subbing in any x values that will make our denominator 0. So we would think of that as a restriction, any x value that makes our denominator 0. Also, if we have an even root, so a square root, a fourth root, a sixth root, something like that, we have to make sure that we don't plug in any x values that would make the number under our radical, called the radicand, negative. We can't plug in any x values that make that value negative. So that would also represent a situation with a restriction. There are other situations where we have restricted domains, but those are going to be the two that apply in most cases that we're going to look at. So let's do a few compositions. The goal is to compose our functions together and then give the domain of each of the resulting functions we get from that composition. So our first function, f of x, is a linear function. G of x is going to be quadratic, and then if h of x is rational, and k of x is a radical function. So let's first start by thinking about the domains for each of these. So for f of x is linear, or more generally we can say it's polynomial. So any polynomial function has a domain of all real numbers. Same thing for g of x, it's quadratic, but more generally it's polynomial, so its domain is all real numbers. Now h of x is rational. So we have the potential to have a 0 in the denominator, which we know is not allowed. So any x value that would make our denominator 0 is going to be excluded from our domain. In this case, the only x value that would do that would be the value 4, so our domain would be all real numbers except the number 4. Now for k of x, it's a little bit different. We want to exclude any value that makes the radicand negative. So one way to think of this is think of it in terms of what would make the radicand 0. It's okay to have a 0 under a square root, but we can think of that as sort of the dividing line between one portion of the number line that does represent the domain and one portion that doesn't. So if we were to plug in a 5 here, 5 minus 5 gives us 0. We can take the square root of 0. So x equals 5 is going to be the cutoff for our domain. If we plug in numbers greater than 5 and then subtract the 5, we end up with a positive number under the radical, which results in our square root being defined. If we plug in anything less than 5, we end up with a negative under the radical, which results in the square root being undefined. So in this case, our domain for this function is going to be all numbers from 5 to infinity, including 5. So just keep that in the back of your head as we progress through our examples. So first composition we want to do is G composed with F in that order. Now keep in mind, this is not the same thing as the composition above because the order does matter. This would be the function G with the function f of x as its input. So we always start on the inside. Order of operation says start inside, work your way out. So f of x is now going to be our input. We're going to replace it with the expression for f of x. So that's going to be g of x minus 6. Now this is a moment where we have to, again, think in terms of domain. So as we compose, remember the domain is going to take into account issues with the inner function and then issues with the final function. So this is now the inner function. Do we have any domain restrictions in this case? Well, in this case, it's a linear function, so its domain is all real numbers, so we don't have any restrictions in this case for this inner function. So now we can just proceed. So this is now telling me to take the function g and then sub in the specific input x minus 6 in place of our generic input. So that's going to be x minus 6 quantity squared plus 3 times the quantity x minus 6. Now it's just a matter of simplifying all of this down. So our first binomial needs to be FOILed, and then we need to distribute our 3. Let me come down here. So we FOIL this out. This is going to be x squared minus 12x plus 36. Distribute our 3. So plus 3x minus 18. And then we need to combine our like terms, so negative 12x and positive 3x combine, and then also the 36 and the negative 18. So our final expression is going to be x squared minus 9x, and then 36 minus 18 is going to be positive 18. So that will be our final function. This is the new function that results from composing the original functions g and f. Now, at the very end, we also have to reconsider any possible restrictions. So we have to think about the function and its kind, the function kind that we ended up with. In this case, this is going to be quadratic, or more generally, it's polynomial, which means that we don't have any restrictions. We can plug in anything we want in place of x. There's no risk of dividing by 0. There's no risk of taking a square root of a negative number. So in this case, we can use any x value we want. That means our domain is going to be all real numbers. Okay, let's look at another example. So f composed with h. This means we're taking the function f and we're plugging in as its input the function h of x. So we need to sub in h of x. H of x in this case was the rational function 1 over x minus 4. So that's going to be f of 1 over x minus 4. Okay, now at this moment, do we have any issues with domain? Here the answer is yes. Remember, we have to make sure that we don't allow our denominator to be 0, so x cannot be 4. So I'm going to star this one, just so I remember to come back to that and figure out what needs to happen with the domain at the very end. So in this case, we will have to deal with a domain restriction. Now we can evaluate our function. So f with this as its specific input. Now remember, f was our linear function, x minus 6. So this is going to be the input that replaces our generic input, x. So that's going to be 1 over x minus 4, all of that minus 6. Now we need to combine these two expressions together. This one has a denominator, this one doesn't, so we need a common denominator. Think of this as 6 over 1 if you need. This now needs to be written with a denominator of x minus 4. So that's going to be 1 over x minus 4 minus 6 times x minus 4 divided by x minus 4. Okay, let's do a couple of steps in one. We need to combine the two numerators, but we also need to distribute the 6, or in this case, maybe distribute a negative 6 instead, so that it takes care of the signs. So 1 minus 6x, and then negative 6 times negative 4, watch your signs here, that's going to be positive 24. And then we combine over that common denominator, so that's going to be x minus 4. Okay, last but not least, combine our like terms in the numerator. So we have a positive 1, a positive 24. So our numerator is going to be negative 6x plus 25 divided by x minus 4. Now, anytime we end up with a rational function, ideally we want to make sure that that can't be fully reduced, that it is reduced as far as it can go. So in the numerator, notice we don't have any common factors besides 1 between those two terms. So that means the numerator is in its fully simplified form. That also means there's nothing we can reduce with that denominator. So that's going to be our final function. Now we also have to consider issues with domain here at the very end. This function has a denominator. That denominator has a potential to be 0. So we also have a domain restriction resulting at this point. So I'm going to star this one as well. Now what I want you to notice though is notice that the denominator we started with was the same as the denominator we ended with. So what that means is that the restrictions we had to deal with here are the same restrictions we have to deal with here. Sometimes we'll have one problem here and then maybe a different problem at the very end. In this case, any restrictions we have to deal with are going to be the same for both the inner function and the final function. So we only need to write the domain based on that one restriction. So in this case, the only thing that would make that denominator 0 is going to be 4. To verify that, we can take our denominator set it equal to 0. In other words, assume what we don't want to happen actually happened, and then solve for the x value that would make that true. In this case, that's going to be x equals 4, so that's going to be our restriction. So our domain is going to be all real numbers except this number. So we can have any input we want from negative infinity to 4, excluding 4, and then we can also have any input we want from positive 4 to positive infinity, again, excluding 4. So this is going to be our domain for our final function. Okay, let's look at a couple more examples. Combining different functions in different ways. Okay, so h composed with g, so that's going to be h of x with g of x as its input. Now g of x, that was our, that was our quadratic, right? So g of x is x squared plus 3x. So that's now going to be the input. So h of x squared plus 3x. No issues with domain here. This is polynomial. Domain is all real numbers. So we're now subbing that into our function h. H was our rational function, so 1 divided by our input minus 4. So this is going to be the input that replaces our x. So 1 divided by our input minus 4. Okay. Do the parentheses matter in this case? No, they don't. We can take them off, and it's still the same function. It still logically means the same thing. So we should drop those off. Now, this is going to be our final function. Do we have issues with domain here? The answer is yes. We now have a denominator. The input didn't have a denominator, but the final function does because we composed into a rational function. So we do have a potential issue with the domain here. We need to restrict any x values that would make this denominator 0. Well, it's not going to be as simple to just look at it and determine what x value or values would make this denominator 0. So we do need to take that extra step of taking our denominator and then setting it equal to 0 and solving for those excluded values. So we have a quadratic equation. This can be factored. So it's going to factor as x plus 4 times x minus 1. If you need to take a minute, pause the video, make sure you can factor this. We're looking for values that multiply to give negative 4 that also add to give positive 3. So that's going to be a positive 4 and a negative 1. So if either of these factors is equal to 0, that means we would get x equals negative 4 and x equals positive 1. So these are going to be the two excluded values, the two values that would make our denominator 0. These will be the exclusions from our domain. So our domain is all real numbers except these two values. Now be careful here. You might want to draw a picture of the domain based on having these restrictions. So here's negative 4. Here's 1. How many intervals does our domain have? Well, we can have anything we want that's less than negative 4. We can have anything we want that's greater than negative 4 but less than 1. And we can also have anything we want that's greater than 1. So we actually have 3 intervals represented as part of our domain. It's tempting to look at these restrictions and keep everything less than negative 4, keep everything greater than 1, but maybe forget the fact that there are values in the middle. In this case, our domain is represented by 3 separate intervals. So we need to include all 3 as part of our domain. So negative infinity to negative 4, union, negative 4 to 1, union, 1 to infinity. That's going to be our domain. Okay, what about k composed with f? So k, I believe that was our radical function, and then f was linear. So k of f of x, let's verify. So f of x is linear, x minus 6. So that's going to be k of x minus 6. Now I'm subbing this in to the function k. So the function k is our radical function. square root of x minus 5, square root of our input minus 5. No issues with the domain. So square root of our input minus 5. And then we can combine these two terms under the radical. Negative 6 combined with negative 5. That's going to give us negative 11. So square root of x minus 11. Now we didn't have any domain issues here, but our final function is now a radical function, and we do have potential issues with the domain with a radical function. So we have to make sure we're not plugging in any x values that would make our radicand a negative number. So x minus 11 must be greater than or equal to 0. That is the only way this expression will be defined in terms of real numbers. So add the 11, move that over. So x is going to be greater than or equal to 11. And if we want to write that in interval notation, maybe draw a picture first, just so we're sure of what that looks like. Here's 11. We want to keep values that are greater than or equal to 11, which means 11 itself can be included. So everything from 11 to positive infinity will be included in our domain. So our domain is going to be all the values from 11 to infinity inclusive. Now, if you struggle to remember what inequality to set up in this situation, here's a trick. Here's how I like to figure out the domain for something that's radical. We know we can't have any negative numbers under the radical. We know 11 is the cutoff because 11 minus 11 would give us 0. The square root of 0 is 0, okay, and that's defined. So that's the cutoff between square roots of positive numbers and square roots of negative numbers. What we have to determine is what values give us positive square roots and what values would give us a square root of a negative number. So once we determine that 11 is the cutoff, pick a test value on either side of that number 11. So maybe just pick 10 and 12. What we want to determine is which one of these results in something that's defined and which one results in something that's undefined. So imagine subbing in a 10. Well, 10 minus 11 is going to give us negative 1. Square root of negative 1 is not defined over the real numbers. So that means this particular input is not going to be part of our domain. Now what about 12? 12 minus 11 would give us positive 1. Square root of positive 1 is 1. It is defined. So this one does work. If 11 is our cutoff, and we know that this test value is going to work in our function, then that means we're going to keep the side of the number line that contains that test value that does work, and we're going to exclude the side of the number line that has the test value that didn't work. So that's a way to figure out a little bit more analytically what sort of issues we're going to have with the domain and what our actual domain is going to be. Okay, let's do one more. Let's do the hard one, if we want to call it the hard one. So h composed with k. So h of k of x. Okay, now k of x, that was a radical function. So let's flip back over. So k of x is square root of x minus 5. So we're taking h of the square root of x minus 5. And then h was our rational function, just to verify. H was 1 over our input minus 4. So 1 over our input minus 4. So this is our final function. We can't combine the negative 5 and the negative 4. One's under the radical, one's not. So they're not like terms. They don't combine. Technically speaking, in some situations you may want to rationalize this expression, which means converting it to an equivalent form that doesn't have any radicals in the denominator. Here we can just leave it. There's no issues with just leaving it there. So our inner function, does our inner function have any domain restrictions? Well, it's a radical function, so yes, it has domain restrictions. So I'm going to star right there, and we'll come back to that. Now what about our final function? Are there domain restrictions here? Yes, in fact, there are two issues represented with our final function. Number one, we have a radical. It's the same radical as the one we had before. So any issues we have here are also represented here. But notice what else we have. We now have a denominator as well. So not only do we have to take care of any issues with that radical, we also have to take care of any issues with the denominator. The denominator can't be 0, and we can't have any negative numbers under our radical. So we actually have two different issues represented with this final function. Now let's start with the radical portion. That's going to eliminate more potential inputs than we'll get from just dealing with the denominator. So square root of x minus 5. We know that x minus 5, our radicand, must be greater than or equal to 0, which means x has to be greater than or equal to 5. And same kind of idea if you want to model it using the number line. 5 is your cutoff. Things that are greater than 5, this will be defined. Things that are less than 5, this will be undefined. So we know automatically that excludes half of the number line, everything less than 5. Now we also need to make sure that this denominator is not 0. If it's 0, we've divided by 0 and we know that's not allowed. So what value or values would make this denominator 0? Well, assume that our denominator was 0. Assume what we don't want to happen did happen. How would that work out? What would x have to be to make that true? Well, we can determine that by solving the equation we get when we set it equal to 0. So add your 4, you're starting outside and then working your way in when you solve an equation. So that's going to give us square root of x minus 5 is equal to positive 4. Now we need to eliminate our radical. The inverse operation for a square root is going to be squaring. So square both sides. That's going to give us x minus 5 is equal to 4 squared, which is 16. And then we can solve for x by moving our 5 over. So that's going to give me x is equal to 21. What does this represent? Well, this represents the one x value that's restricted because it makes the denominator 0. We can verify that this makes the denominator 0 by just plugging it back in and seeing what happens. So if you plug in a 21, well, 21 minus 5 is going to give you 16. Square root of 16 is 4, and then 4 minus 4 is 0, which again is what we don't want to happen. So this is our restriction. So both of these issues have to be taken into account when we write the actual domain. So here's another good situation to use a number line. What does our domain look like in light of the fact that we have two different restrictions? Well, notice the numbers in question. The important numbers here are going to be 5 and 21. So let's mark those on the number line. Here's 5, here's 21. Make sure you write them in the correct order. Okay, so x has to be greater than or equal to 5, but it can't be equal to 21. So notice 21 is included in this interval. So our actual domain is going to be this interval except the number 21. So we can have everything from 5 to 21, skip 21, and then we can have everything from 21 to infinity. So that's going to be two separate intervals. Notice we have a bracket with 5 because 5 is included. Equality is part of that inequality. But we have parentheses everywhere else because number 1, we want to exclude 21, and then number 2, we always use parentheses with positive and negative infinity. So our domain is going to be 5 inclusive to 21 exclusive, union 21 to infinity. That is our domain. So this particular example takes into account both of our issues with domain. So once you get to the very end, if you have a function like this, break it down. You have to think about the two different issues. The radical represents one issue, the denominator represents a different issue. Think about them individually, and then if it helps, maybe draw a picture to model how those restrictions are going to factor in and how they're going to work together. Okay, so let's talk a little bit about function decomposition. We know how to compose functions. Well, what would decomposing mean? Ultimately, decomposing a function reverses the process of function composition. So when we compose two functions together, we're taking two functions and we're combining them. If we decompose, essentially we're taking what we can think of as the answer for a composition, and we're working our way backwards. We're taking it and we're breaking it up into those original two functions that would have combined together to give us that final function. So composition is going to be important for calculus from the standpoint of recognizing a composition. But ultimately, we're going to use decomposition a little bit more in order to take a more complicated function and break it down into what we're going to think of as an inner and an outer function, but specifically two functions that are simpler than the original function. So we're going to use the skill of decomposition when we start with a function that's a little bit more complicated, that has a lot of operations represented, and decomposition is going to allow us to take a more complicated function and break it down into simpler functions that don't have as many operations represented. Now sometimes it's going to be fairly obvious what we can think of as inner and outer if there's truly sort of an outside operation that's easy to identify. We're typically going to use that as our outer function, and then anything that we can think of as being inside that operation represents our inner function. But if we have a function where it's not obvious, or the skill of identifying inner versus outer is just something that's difficult for you, we can actually use the order of operations to analyze the function's operations, all the different steps we take, the order they come in, and then what we're going to do is we're going to group them. The way we group them is then going to allow us to assign operations to our inner function and to our outer function. And the good news is you can always check your work after you do a decomposition. If you take your two functions, your inner function and your outer function, and you compose them, you should end up with that more complicated function that you started with. If you do, that means you have a correct decomposition. If you don't, it means your decomposition is incorrect. Maybe you did operations out of order, maybe you're missing an operation, something like that, but you know to go back and check your work. Okay, so given each of our more complicated functions, h of x, we want to find two functions f and g such that h of x could be written as f composed with g of x. So let's be careful here. We have to think of which one is which in terms of inner and outer. Remember, f composed with g means f with g of x as its input. So that means that g is going to be our inner function, and then f is going to be our outer function. The ordering very much matters because remember, composition is not commutative. Changing the order of your functions when you compose them typically results in a different final function. So we do have to be careful about what we're treating as the inner function and what we're treating as the outer function. So here's our more complicated function. Notice we have four operations represented. We have absolute value, we have a multiplication by 2, we have an exponent of 2, and then we have a subtraction. So 4 operations in total. Now here you may be able to see what you can think of as outer. Notice the absolute value is on the outside of this expression 2x squared minus 5. So we can think of that as being the outer operation, which then can be attributed to an outer function. But suppose, again, you don't really have that skill, it's a little bit more difficult, seeing outer versus inner is a little bit more challenging to you. Here's a way we can methodically go through and determine what operations go where and how to decompose into our functions f and g. What I want to do is I want to make a list of each of the operations represented in this function based on the order they would be applied in from order of operations. So I want you to imagine for a moment that you're plugging in a specific x value. Maybe just call it 0 or 1 if you need a specific number. You're plugging in something to your function. What I want you to think about is if you were to plug in a value, in what order would you simplify all of the operations represented by this function? Well, if you were to plug in a number here, the first thing you would have to do is apply the exponent based on order of operations. So the first thing you would do is square. So if we're going to make a list of the order of operations for these particular operations, the first thing we would apply would be this exponent of 2. Okay, so once we take our input and square it, we're then going to take the result and multiply it by 2. So that would be the next step in the order, multiply by 2. We would take the result of that and subtract 5. And then the final operation we would apply would be that absolute value. And so essentially this takes us from the innermost operation to the outermost operation. Here's how we use this to decompose. What we can do is we can take one or more of these operations and group them, and then write a function that only applies that operation to an input. So suppose we want our outer function f to only contain the outermost operation. Well, the outermost operation is absolute value. So when we write this outer function f, we're going to write it as a function that takes an input and only applies this absolute value operation to the input. So that means our function f of x is just going to be a function that applies absolute value. So we're going to write f of x as just the function that applies absolute value to the input x. Well, if that's f of x, then all of the other operations will be represented as part of our inner function. So our inner function is going to be the function that applies an exponent of 2, a multiplication by 2, and then a subtraction of 5 in that order. So our inner function takes an input, x, it applies an exponent of 2, so we would take our input and square it. It takes that and multiplies that by 2, so multiply the result by 2, and then it takes the result of that and subtracts 5, so minus 5. This would be a decomposition. Imagine taking g of x, our inner function, and composing it with f, plugging it into this function f. Well, if we plugged this function into the function f, that says take the absolute value and apply it to whatever input you're plugging in. Well, if you take the absolute value and apply it to this input, you end up with the absolute value of 2x squared minus 5, which is our original function. So this would be considered a decomposition. This would be an outer function and an inner function. Now what I want you to keep in mind, this is kind of strange. Typically there's one answer in math, right? Or maybe there's a combination of answers, but all of them are necessary. Well, when it comes to something like decomposition, in a lot of situations there's more than one correct answer. So how would we come up with another correct answer? Well, for this particular decomposition, notice we just took one operation as part of our outer function, and then the rest of operations were represented in our inner function. Well, what if instead of just having one operation for the outer function, we used two operations? So rather than grouping it as 3 and 1, maybe group it as 2 and 2. How would that change our outer function? Well, in that case, our outer function would have a subtraction of 5 and then an absolute value. So that means our new outer function would take our input, we would subtract 5, so minus 5, and then we would take the absolute value. Excuse me. So that could also be considered an outer function, but notice it includes two of the operations we need. Well, if that's our outer function, that means the inner function is only going to include the first two, not the first three operations. So our inner function would be the function that takes our input, applies an exponent of 2, so we would take x and we would square it, and then takes the result and multiplies by 2. So that would be another way of writing our inner function. What happens if we compose these two together? Well, this would become the input for f, this would replace our x, so we would have the absolute value of 2x squared minus 5, which again matches our original function. Both of these are technically correct. Both would be considered correct decompositions. Now, once you get to calculus and you're using this skill to actually decompose functions in the context of the problem, typically this is going to be the decomposition you're going to want. The one that takes the outermost function, breaks it down into a function that only has one operation represented, and then everything else is part of the inner function. But keep in mind, you can decompose in more than one way and potentially end up with another correct decomposition. Okay, let's look at another example. And we'll just do one decomposition for this one and then for our last example. So here's h of x. We have the cube root of the quantity 5x plus 1. So maybe you see the root as being outer, and you can think of that as your outermost function. But if we want to be more methodical, go through order of operations. Again, think of plugging in an input, replacing x with a specific input, and following order of operations to simplify. Well, we would take our input. The first thing we do is multiply by 5. So our first operation, we multiply by 5. For the second operation, we would add 1. And that would fully simplify the radicand. And then we would take the cube root as our final operation. So this is our innermost operation. This is our outermost operation. So if we want to decompose this function into an inner and an outer function, the outer function could just represent the cube root, which means our outer function is going to take an input x, and it's just going to apply the cube root to that input. If this one operation is represented for our outer function, the other two have to be represented by our inner function. So that means g of x would take our input, it would multiply it by 5, and then it would add 1. So take your input, multiply it by 5, and then take the result of that and add 1. Again, imagine composing these two together. G of x composed into f of x would take 5x plus 1, and it would make that the input for our cube root function, which again would result in the original function we started with. Now for these two, I would argue that there's a fairly clear inner and outer sequence of operations. The absolute value is outside of everything else. The cube root is outside of everything else. Depending on the type of function we have, it may not be as obvious what is considered outside and what is considered inside, particularly in terms of defining specific operations. So here's an example where it may not be as obvious what you could treat as an inner and an outer function, and using the order of operations is going to be a little bit more important. So suppose we have a rational function that we want to decompose. We actually have two operations represented here, or technically we think of it as 3, but we're just gonna treat it as 2. Imagine plugging in your input, x. So we're replacing something with x, or replacing x with something else. The first thing we would do would be to add 4 in the denominator. Think of numerator and denominator as being grouped within their own sets of parentheses. So if you have a rational function, simplifying the whole numerator and simplifying the whole denominator has to take place before you execute the actual division. So we add 4, and I'm going to put a note in the denominator. And then we would take the result and we would divide that into 5. So divide into 5. Now we're not dividing by 5, we're dividing into 5. So it's 5 divided by this result. So this would be our inner operation. This would be our outer operation. Now one other way to think about it, if you wanted to think of it in terms of 3, you could also think of maybe just dividing into 1 and then multiplying the result by 5. But that's not officially necessary. We can just think of it as dividing into 5. So if we only have 2 operations, that means there's only one way to decompose the function, because there's only one thing that's inner, there's only one thing that's outer. So in this case, our outer function takes an input and divides it into 5. So it would take our input x and divide it into 5. Well, if that's the outer function, the inner function needs to include whatever operations are left. And in this case, the only operation is going to be an addition of 4. So we would take our input, and it's going to add on 4. Again, double check. If we were to compose g of x into f of x, x plus 4 replaces our generic input for f, which would then give us 5 over x plus 4, which is the original function we started with. So all 3 of these concepts, the concept of the difference quotient, how we evaluate that, simplify that, and then function composition, joining functions together, function decomposition, breaking functions into pieces, all 3 of these are going to be essential concepts that you're going to use regularly throughout calculus.